Every programming language has its own set of libraries, many of which are the sole focus of a group of very talented developers. For example, there exist libraries for cryptography in pretty much every popular language. What if we combine all the developers working on each language-specific crypto library and put them all together? That might actually yield just enough brainpower to center a div or even quit Vim. But more importantly, all of them can focus their efforts on one crypto library instead of having the language fragmentation that we have today. In this video, we're going to write a library in Rust and publish it to the WebAssembly Package Manager such that it can be consumed by anybody using a language supported by the sponsor of today's video, which is Wasmer. Wasmer supports 17 different languages. Some of those languages get direct integration with their respective package managers. For example, if I have a Node.js project, the WebAssembly Package Manager command line tool can add the universal library directly as a Node module. If I have a Python project, I can add the universal library directly as a pip package. Then the library can be consumed pretty much seamlessly as if it were written directly in the consuming language. Again, this video is sponsored by Wasmer, who I think are doing some really interesting things in the WebAssembly space. Let's take a look at how to create and publish a universal library. It's probably a lot simpler than you think. The first thing we're going to do is create the project like we would any other Rust projects. We'll do cargo new -- lib, and we'll call it universal crypto. Now we're not going to create a full-blown crypto library in this video. We're just going to create a very, very simple one with one SHA-2 function. But using this method, you could theoretically create an entire crypto library if you wanted to. Now we'll go ahead and cd into the library. The first crate that we're going to add to our library is y-bindgen rust, and you'll see what that's for in a minute, but we'll do cargo add y-bindgen rust. Now the starting point of this library is the Y file, and WAI stands for WebAssembly Interface, and Y is a full-blown interface descriptor language, or IDL. It's kind of like gRPC or protobuf, if you're familiar with those, but basically it allows us to specify the constructs and functions that our library is going to implement, and two things come out of that file. One is compile time checks for our library, so it's going to, at compile time, make sure that we're implementing everything that we say that we're implementing in the Y file. And on the consuming side, it's going to be able to generate language-specific bindings for all the things that we say that we're going to implement in our Y file for each of those 17 languages that's supported by Wasmer. So we'll go ahead and create that file. We'll call it universal crypto Y, and we're going to open it in VS Code. And again, we're going to only implement one function in this crypto library for now to keep things really simple. And it's going to compute a SHA-256 hash of the given string. And normally a crypto library would take binary data as input and give binary data as output. To keep things ultra simple, we're going to have our function actually take a string and return a string. So it's going to be called hash. And I'll go over more of the syntax of this file in a little bit, but it's going to take a string and return a string. Now let's open up our lib.rs file, and we're going to delete everything that we have here. And we're going to call a macro in the y-bindgen rust crate. So we're going to do y-bindgen rust. And the macro is called export. And we're going to specify the name of our Y file. So universal crypto.y. Save the file. Now let's go ahead and compile this and see what happens. And we're going to do cargo expand to expand the macros that we've written. And we can see the code generated by this macro. We can see it's basically creating a trait called universal crypto with the expectation that we implement this trait. So it expects a type universal crypto to be in the module that we created, and it expects that to implement universal crypto, the trait, which is defined in the code that's generated from the macro. So what it's saying is that you need to have a struct in your module that implements this trait that has this hash function that comes from the .y file that we defined a minute ago. So that's kind of cool. So it's ensuring that we implement everything that we say that we're going to implement in the .y file. There are two crates that we're going to use to help implement our SHA-256 function, and one is called secret toolkit crypto. So we're going to add that real quick. Cargo add secret toolkit crypto. The other crate that we're going to use is base64. So cargo add base64. Now we're ready to implement our function. Again, remember the error. It said no type universal crypto in module super. So we're going to create a struct universal crypto. It's not going to have any fields or anything, but it is going to have an implementation of the universal crypto trait, which is defined by the generated code from this export macro. Okay, so again, the function is going to be called hash, and it's going to have a string as input. This IDL has concept of a string, and that string will get translated to all the various language-specific strings. So in the case of Rust, that translates to the string type. And we're just going to do base64 encode and SHA-256 input as bytes. We do need to make a use statement for this secret toolkit crypto crate. SHA-256. And we actually need to add the hash feature in our cargo toml. So this is version and features. Okay, pretty straightforward. So to recap, this macro, this export macro, generates a trait called universal crypto. And that trait has a function or a method that we define in our Y file. It also expects a type in the module here that implements that universal crypto trait. So that's what we're doing here. There is one more thing we need to do before we can build this, and that's to specify a crate type. So we'll put a lib section in our cargo toml and do crate type and cdylib and rlib. Then we'll do cargo build and then target wasm32 unknown unknown. Cool, and we should get a wasm file in the build directory. See target slash and then debug. And we do. We can see universalcrypto.wasm there. There is a way to see inside that wasm file and see what's inside there. And if you haven't already, now would be a good time to install wasmer and wapm. So on a Mac, you can just do brew install wasmer wapm. If you're not on a Mac, you can just go to the wapm.io website and there's a command there that you can copy and paste into your terminal. I already have it, as you can see. But now that we have those tools, we can just do wasmer inspect and then the path to the wasm file. And we can see it exports a function called hash. So now that we have our library built, we can actually publish this directly to the WebAssembly Package Manager. A while back, I made a full video on WebAssembly Package Manager that I'll put a link to in the description if you're interested in that. But all you need to know for now is that I can publish to the WebAssembly Package Manager using cargo wapm. But before I do that, there's some more stuff I need to put in the cargo toml. I'm going to create a new section called package.metadata.wapm, and this is going to be some metadata that's used by cargo wapm to publish it. We're going to specify a namespace. This is basically your username in the WebAssembly Package Manager. I'm going to do ABI as is none because we're not using one. And then we're going to say bindings equals, and we'll specify our Y file here. That should be all we need to go ahead and publish this package to the WebAssembly Package Manager. But in order to use cargo wapm, I need to install a helper called cargo wapm. So we'll do cargo install cargo-wapm. Cool, and if you haven't already, you'll need to log in with the WebAssembly Package Manager. And the easiest way to do that is log into the wapm.io website and go to settings and then access tokens and create a token. Universal library, and it'll give you the exact command to use to log in. So I'll just copy that, paste it into the terminal. Boom, we're good to go. So now we should be able to do cargo wapm. The description field in the cargo toml wasn't set. Okay, so yeah, the description field is actually in the package section. So we'll do universal crypto library. And that should be it. So it was successfully published package cttm/universal crypto at 0.1.0. One thing to note is you need to change the version number of the package if you want to upload another revision. So if I'm making changes and testing stuff out and I publish and then I make some more changes and I want to publish again, if you don't change the version number, you're going to get an error here. So just something to watch out for. So now if I go to wapm.io and my profile, I can see my library here. And it'll actually give me the npm and Python commands to install it into the consuming application. More on that in a minute. That's it. We've written a library in Rust and published it such that it can be consumed by pretty much any other language. I did mention that Wasmer supports 17 languages, and some of those get first-class support with package manager integration. One of those is JavaScript. So I can have a node project. I can add my module as a node dependency using the wapm command line tool. Let me show you how to do that. First, we're going to make the app. We're going to cd into the project, and we're going to use Yarn to set up the scaffolding for the project. And if you're not familiar with Yarn, it's basically an alternative to npm in the JavaScript world. So we'll do npm init --yes. And so now we get a package JSON. Let's go ahead and open that up in our IDE. We're just going to add a main field in package.json so we can tell it how to run this thing. Okay, and then let's just create an index.js in the bin directory. Forgot to add a comma here. Okay, now is the really cool part. I can run wasmer add -- yarn and then my namespace and then the package name. And it's going to add my WebAssembly package essentially as a native node package. And if I go into my index.js, I can import that hash function by doing import bindings and then the node module, which is universal crypto. And going back here, so I can actually ls in node modules and I can see my module there. It looks just like a regular node module with a package.json and everything. So Wasmer takes care of setting up all the kind of boilerplate necessary to invoke that WebAssembly. And to my consuming application, it just looks like I'm using a regular node module. That's really cool. The other thing we need to do in package.json is to specify that this is a module. So we'll do type module. Now we're at our main function, which is going to be asynchronous because we're going to call await in the first line. So we'll do const. We're going to get that universal crypto object that we create in our library. UC equals await bindings.universal crypto. So now this UC object will have all the functions that we define in that universal crypto object in our library. It has that hash function that we define. So we can do a console.log and UC.hash, and then we can specify the argument that was passed into this program, which is actually going to be index 2, because in node projects, the first argument is the application name. The second argument is what you're actually running. And then the third argument is actually what got passed into the program. So we'll do process.argv and index 2. So that should give us the string that the user specified when running the program. And all we need to do now is call the main function, and then we can go to our terminal and do node. We're in the project directory. We'll do node dot for the current directory and then pass in the string that we want to take the hash of, which is ASDF, and we get a result. To verify that result, this isn't really the point of the video to get the hash just right. It's just to be able to invoke a function that we declared in a universal library or defined in a universal library. But to verify it, we can do echo-n ASDF and then pipe that to OpenSSL, take the digest of it and output in binary format, and then pipe that to base64, which should give us a string, and we get the same string. So we know our SHA-256 is working properly. So that's how we consume a WebAssembly universal library from a JavaScript project. Again, you can do this in any of the 17 languages supported by Wasmer, but there are some languages like JavaScript and Python that get first-class package manager integration. Okay, so we kind of gloss over Y, or the WebAssembly interface language. We only put one function in there, but it turns out you can do a lot more in the Y file. It's actually a pretty powerful syntax. So let's look at a few more constructs that we can define in the Y file. There is some pretty comprehensive documentation for the WebAssembly interface definition language in this GitHub repository here. I'll put a link to it in the video description below if you want to take a look at it, but there's a lot of stuff in here, but we're just going to take a look at some of the highlights. There is syntax highlighting available for Y files, which you are going to want if you're going to work with them. There's a VS Code plugin called just simply WebAssembly that will give you syntax highlighting for Y files. There's a few plugins with very, very similar name. Make sure you get the one that's created by the WebAssembly Foundation. And if you click on the repository link, you should get the GitHub repository underneath Wasmer.io. Also, it's the one with the most downloads, at least at the time this video is being recorded. I don't anticipate that changing by the time you watch this. So yeah, this is the one you want. Again, all we have defined so far is this hash function. We can also define a struct class-like structure in Y terms. It's called a record. So we can do something like record crab, and then it has two fields, an age and a name. And then we can define a function that uses that. So we can do get Ferris, and that's a function that returns a crab. And then now in our Rust implementation, we can see we have errors. It's saying that there's a missing getFerris implementation. That's because the trait that the macro expands to now includes that getFerris method. So we've got to implement that. Then we do function getFerris, and that's going to not take any parameters, and it's going to return a crab. And we actually need to pull in that struct that was defined in the Y file. We don't want to define it here because it's defined in the Y file. So to do that, we can do use universal crypto crab. And at this point, we can return the crab. So we'll define a new crab with an age and a name. Cool, so that's what that looks like. So yeah, this record construct in the Y file is kind of like a struct or a class in most modern programming languages. Another construct that you can use when you have some internal state that the library is tracking, but you don't want to necessarily expose that internal state to the consumer, but you want to expose methods that mutate that state to the consumer. A construct that you can use for that scenario is called resource. So we could have resource speech, And that can have a method is Ferris here. And that returns a Boolean. And so the library would manage the internal state for the beach. So it might have a count of the crabs on the beach or something, or it would search through the set of crabs that are on the beach and see if there's one with the name Ferris, but it wouldn't expose that internal state, that vector of crabs, to the consumer of the library. Okay, so back in our Rust library, we need to define that a struct for that resource because we're not defining the structure of that resource in the Y file. We actually need to define it in our Rust code. So we'll do pub struct beach, and then the only internal state is that vector of crabs. So gonna be a vector of crab. And then we can define the implementation for that resource. So again, similar to this universal crypto, when we have a resource, the macro will expand to include a trait called beach that has all the methods that we define in that resource. And it's our responsibility to implement all those methods. So we can do function is Ferris here. And we do get a reference to self in the case of resource. And we can do self.crabs, iter, find. So that's how you use resource. The next thing that we can define in the Y file is a C-style enum, and that's using the keyword enum. And a C-style enum is just a set of possible variants that the value can be. There's no fancy stuff like tuple structs, or in Rust, each enum variant can be a tuple struct or a struct with named fields. Not so with C-style variants. So we could do a crustacean, and the crustacean can be a crab, a lobster, a crawfish, or a shrimp. And we can define a function, get a crustacean, that returns a crustacean. Back in our Rust code, we need to import that crustacean enum. So we can, it's very similar to crab. And then we need to define that get a crustacean function that we saw. We'll do it down here. And we'll just return a shrimp. That's how you define a C-style enum in the Y file. But we can also define Rust-style enums too. You can define Rust-style enums using the variant keyword. So we can do variant optional crustacean, and each variant can have a tuple associated with it. So there can be a sum or a none. And we'll define a method that uses that optional crustacean. Make the font a little smaller here. Sorry folks on your cell phone. So back in our Rust code, that would look something like this. Get optional crustacean. And we do have to create a use statement for optional crustacean as well. And that should do it. So that's how you create Rust style enums with the variant keyword. But the cool thing is it turns out that Y includes a built-in optional type. So we can use that instead, or it's actually called option. So we can actually change this to be option of crustacean. And the cool thing is that gets translated to the native Rust option type. So I can change this to option crustacean. And then instead of doing this, I can just do some crustacean shrimp. Cool. So no need to actually define your own optional type using the Rust style enums. I just wanted to show that as an example of a Rust style enum. There's a built-in option type for you to use. There is also a built-in list type. So I can do get crustacean list. And that can return me a list of crustaceans. Get list. And that actually gets, in the Rust side of things, that actually gets translated to a vector. So vec of, and then we can return, use the vector macro and return our vector. So that's list. There's also something called expected, which will translate to the native Rust result type. So let's look at that. We can define our own error types in the Y file, but we'll just do an alias to string for our error type. So we can do type some error, and we'll make that a string. And then we'll do another function that could fail. And that's going to return expected of crustacean. And just like the Rust result type, we need to specify the error type here. So we'll do some error. And again, like I said in the Rust code, that actually gets translated to a native result type. We'll do function. And we do need to import that error or create a use statement for that some error. This one's not there anymore. And we can just return OK of the shrimp. So yeah, expected keyword translates to a result on the Rust side of things. Anyway, you get the idea. You can create a lot of powerful constructs in the Y file. And again, that'll get translated to the Rust equivalent of that construct on the library side of things. And then the bindings in each of those 17 libraries that we talked about will accommodate, or there'll be a translation for each of those 17 bindings. So that's really cool. So I can effectively create a schema or a contract or an interface from my universal library that will be translated into what's idiomatic in each of those 17 languages. So you really can create a library that accepts and returns any kind of data that you want. So yeah, it turns out that a lot of aspects of WebAssembly that make it great for front-end development also make it great for other things like back-end development, and like we saw in this video, creating libraries that can be consumed from many different programming languages. Consumption that in some cases feels like you're consuming a library written in the same language. We considered a cryptography use case in this video, but it's easy to imagine having these universal libraries for things like parsers, codecs, numerical computation, and even machine learning. Also, there's an actual SHA-2 library that's already published to WAPM that's a bit more capable than the one we created in this video. I'll include a link to that in the description if you're interested. If you're as interested in the WebAssembly space as I am, make sure to check out this video I did that gives a more broad overview of WASMer and the WebAssembly Package Manager. Thanks for watching, and we'll see you in the next one.